We're going to wrap up our discussion of covalent bonding by talking about molecular orbitals and orbital hybridization. So before we get into molecular orbitals, let's remember our atomic orbitals. So S, P, D, and F orbitals are the different types of regions of space or energy fields of electrons. They get increasingly complex as you get to higher and higher energy because, again, you've got a lot of things trying to get as close as they can to the nucleus while trying to get as far away as they can from each other. And these are the spaces that they're going to try to occupy to do that. So with this idea of atomic orbitals in mind, let's talk about molecular orbitals. So here we have two hydrogen atoms. Their electrons are in s orbitals. And so when those two hydrogen atoms form their diatomic molecule, those s orbitals are going to, in fact, overlap and create what is called a molecular orbital. And the molecular orbital slightly changes shape. We've got the cloud to represent the shared pair of electrons and where they're likely to be found. Notice that they're equally distributed between both nuclei, but there is more kind of space in that orbital between the nuclei that are sharing the pair of electrons rather than on either side. This is what we refer to as a sigma bond. And a sigma bond comes from this idea of overlapping two objects together that are going to, when they overlap, their initial point of contact will be a single point. Think about it as two spheres touching. Two spheres can only touch at a single point, and so that's what a sigma bond represents, kind of a single point of overlap. We can also take a look here at a fluorine molecule. And a fluorine molecule is going to bond not by overlapping s orbitals, but by overlapping p orbitals. And so the shared pair of electrons would be in p orbitals in fluorine's valence electrons. When they overlap, they produce a molecular orbital. Once again, where those kind of outside lobes of the p orbitals are going to shrink a little bit, and the insides are going to overlap to create this shared space in between the fluorine nuclei. This is also considered a sigma bond because, again, there's one point of contact. And if you were to zoom in at that point of contact, given the shape of p orbitals, you would find that you would not be able to tell if you were zoomed in super close whether it was two spheres touching or two p orbitals touching, because you're going to have kind of a similar curvature shape at that point of contact. That said, in order to get sigma bonds, the first three ways we're going to talk about are s orbitals overlapping with s orbitals, an s orbital overlapping with a p orbital, or two p orbitals overlapping at a single point of contact. P orbitals come in three types, though. We have x, we have y, and we have z. And so if those p orbitals rather than are oriented end to end, but oriented side to side, when they overlap, you're going to get what's known as a pi bond. And so when those two p orbitals overlap, what they produce is two regions of space above and below the nucleus. This will only happen after a sigma bond has taken place between the two nuclei. So all single bonds will always be sigma bonds. If you have a double bond, one will be a sigma and one will be a pi. And here's kind of a representation of what's going on there. Here we're just showing the 2py and the 2px. The 2pz would be coming out of the screen and going into the screen. But in order for that 2py to overlap and form the pi bond above and below your nuclei, the 2px would also have to overlap with one another, and you would have to have that sigma bond at the same time. So your first overlap here in the 2px, for instance, would be our sigma bond. Then our overlap here of the 2py, that would be our pi bond. So every sigma bond, or every single bond is a sigma bond. A double bond would be a sigma and a pi, and a triple bond would be a sigma and 2 pi. So if we were going to get that triple bond, that z orbital kind of coming out and going into the screen would have to overlap sideways at that 2 points of contact. which is kind of the characteristic of the pi bond, is that rather than one point, there's 2 points of contact. This is also why the quadruple bond can't happen. One, there are no other p orbitals. Two, there's no more room in the region of space between those two nuclei. You've got above and below, you've got a front, behind, you've got in between, and there would be no other way to squeeze any more negative charge in that region of space. And so the triple bond is kind of our max because of that geometry. All right, so those are molecular orbitals, sigma and pi bonds. Let's talk about them in context of what's called orbital hybridization. And so what I would like you to do now is would like you to draw a Lewis structure, sorry, not a Lewis structure, an Aufbau diagram of carbon. So carbon has 6 electrons, 4 valence electrons, and draw an Aufbau diagram out on your paper. Go ahead and pause the video and do that. Okay, hopefully if you did so, you got this. And at some point, maybe some of you were wondering, back when we were doing Lewis structures, why didn't we draw carbon like that? Carbon's got 4 valence electrons, 2 of them are paired and 2 of them are unpaired, and yet this is not the structure that we produced for carbon. Instead, we said that carbon does this. Well, it does in fact do that, and it does it by moving an electron from the 1s into the p. And so there are in fact 4 unpaired electrons in most carbon compounds. Now, in order to do that, it has to go through some changes, because this is a slight violation of the Aufbau principle in that you don't have a full 2s and you're moving that electron into the 2p, which is particularly complicated in lower energy levels because there's a big energy difference between the 2s and the 2p. So how does carbon account for this? Well, it goes through what's called orbital hybridization. And in orbital hybridization, it's going to take those 4 orbitals and it's going to combine them into 4 equal energy orbitals called sp hybridized orbitals. And the sp hybridized orbitals look like this. So essentially one side of the kind of p orbital dumbbell gets bigger and the other side gets a little bit smaller. And when all 4 of these orbitals hybridize, you get what's called sp3 hybridization. And sp3 hybridization is how you end up with 4 bonds on a carbon, 4 opportunities, 4 unpaired electrons that can form bonds that are all, of course, 109.5 degrees apart. Again, nothing magic about 109.5 degrees. It's geometry. That's how far away 4 things have to get in 3-dimensional space to be as far away as they can from each other. Why do they want to be as far away as they can? Well, they are electrons and they repel. And so that is your sp3 hybridization. And that's why the tetrahedral exists. And if we're looking at something like our methane molecule CH4, well, then what's going to happen is you're going to get molecular orbitals on all of those sp3 hybridized orbitals with hydrogen. They're going to overlap. You're going to have the shared pair of electrons, and this is where you get the tetrahedral for CH4, which allows us to extend ever so slightly our definition of sigma bonds. So you can also get sigma bonds with sp hybridized orbitals or sp hybridized orbitals and s orbitals, or potentially, which we don't have on the screen here, an sp hybridized orbital and a p orbital, if, say, for instance, one of those H's were a chlorine. And so that's what sp3 hybridization looks like in the context of a molecule. Well, what happens if there's a double bond between the carbons? If there's a double bond between the carbons, you can only form a double bond with a pi bond. And a pi bond in the molecules that we're considering is only going to be able to form between 2 p orbitals. And so in order for this carbon compound to have a double bond between the carbons, one of those p orbitals is going to have to be left behind. So you're not going to get full hybridization. And so this is referred to as sp2 hybridization. And in sp2 hybridization, two of the p orbitals and one of the s orbitals hybridize. You're going to get the single sigma bond with sp2 hybridized orbitals between the carbons. You're going to get 4 more sigma bonds between sp orbitals and hydrogen, and then the double bond is going to be a pi bond with that pz orbital that got left behind, or a px orbital or a py orbital. Which one it is doesn't really matter. You're just going to leave one of those orbitals behind to form the double bond. Let's look at what happens then when you get a triple bond. Well, when you get a triple bond, you need 2 p orbitals to be left behind. So you're going to get that p orbital that's going up and down in our picture here, and then there's one that is not drawn that's going to go into the screen and come out of the screen. Remember, we have x, y, and z. And so under these circumstances, you're only going to hybridize an s and a p. And so that would be sp hybridization. You're going to get the sigma bond between the sp orbitals, sigma bond with hydrogen in the sp orbitals, and then our second bond between the carbons is going to be that p orbital that's going up and down. The triple bond, the third one, is another p orbital that we can only show here on projection, kind of coming out at you, going into the board, and so the overlap to form that pi bond is going to be there. Okay, so what does this look like in practice? Well, you should, as an initial stage of kind of grappling with these concepts, be able to look at a compound like this, which is a fairly large organic molecule, and see if you can sort out the type of hybridization that's going on in each of these carbons. And so you're going to look at it in terms of double bonds and triple bonds, and how many p orbitals need to be unhybridized to figure out how many p orbitals are going to be hybridized. So you should take a second and draw this molecule out on your paper. Write down C1 to C6, and then you should go through and see if you can predict the hybridization. So go ahead and pause the video and do that, and then when you come back, we'll go over the answers. Okay, so let's take a look at them. So we're looking at C1. Carbon has 3 sigma bonds and 1 pi bond. Remember, every double bond is a sigma and a pi. Sigma bonds mean hybridization. Pi bonds mean p orbital that has not been hybridized. So that 1 pi bond with that double bond means you're only going to get 2 p orbitals hybridized. So that C1 is going to have to be sp2 hybridization. All right, let's take a look at C2. C2 has 2 double bonds. So each of those is going to be sigma and pi. So it's going to have 2 pi bonds, which means it needs 2 p orbitals held behind. That means only one of them is going to go through hybridization. It means you're going to get sp hybridization on C2. Maybe you have noticed by symmetry that C3 and C1 are essentially the same arrangement. 1 p orbital has to be left behind. The other 2 get hybridized, so that's sp2 hybridization. Carbon number 4 has a sigma bond between 4 and 3, and it has a sigma and 2 pi's between 4 and 5. 2 pi's means 2 p orbitals need to be left behind, and so you get sp hybridization. And of course, C5 is just the mirror image of C4. C6, 4 sigma bonds, means everything is hybridized. There are no pi bonds at all. So that's your sp3 hybridization. If you want to go kind of the extra step here, you could look at each of those carbons and see if you could predict molecular shapes around those carbons. Trigonal planar, tetrahedral, linear, pyramidal, that kind of thing. You can predict bond angles between those molecules, because all of this stuff kind of ties together at this point. The hybridization tells us something about the orientation of the electrons, which tells us something about the three-dimensional shape, which tells us whether or not we have polar or nonpolar molecules, depending on the bonds. All of these ideas tie together as we kind of get to this last little step in understanding covalent compounds.